Hi Jacob, I've been thinking about your problem over the weekend, and I have come up with the answer as to why the bottom force F will always end up being the right length and the right length that I've indicated on this diagram. Now, before I actually show you why this works, let's just take something about angles into consideration. So, if I've got a triangle here, and that's 20 degrees, and maybe that's 10 meters long, if I put that triangle over here, and then I construct a larger triangle, and this is now 100 meters long, well, it's still possible for that angle to be 20 degrees. So if I increase the lengths on a triangle, or if I increase the lengths of any shape, it doesn't necessarily change any of the angles in the triangle. So you can have a 500 kilometer long line that's still at an angle of 20 degrees to the horizontal. So when we change the lengths of vectors, if we're doing that on a similar scale to all sides of the triangle, then it's not going to affect any of the angles or any of the magnitudes we get after we perform a sine, cos, and tan. Now, let's just think about this problem and why the angle of repose works. Now, your question was, how do I know that this vector here, which we got by picking up this vector and moving it down to here, how do we know, right, that it's appropriate to draw it this long? How come it's not that long and I draw the angle up there? Or how come it's not this long and I draw it up there? And it's a good question. Let's have a look, though, at some force resolving and some misconceptions about this diagram. So, when we're doing a question like this, we've said that the angle of repose method is quicker, and it only is quicker if we are acting a force on an object on an inclined plane at a horizontal. It's much easier to do the normal way if the force is acting this way. So, just so we know, this method we're about to go through only works when the force, is being put on the object at a horizontal that's already on an inclined plane. Right, so let's just go and calculate some forces. So I'm just going to add on here, this green force here is my force normal. Now, a misconception that might have led to your confusion is what on earth is contributing to this normal force in this diagram. So the normal force, right, the force normal, is equal to everything that's acting downwards, and by downwards I mean downwards this way. So everything acting vertically down contributes to the normal force. So not only is it our normal mg cos theta, in this instance mg cos 20, but also this angle here, mg sine 20. So plus mg sine 20, right? So the normal force, that green force on this diagram, not only has been contributed to by mg cos 20, which is the weight force acting downwards on the object, but also the downwards or the vertical component of the force actually acting upon the object. So this normal force is the object's normal force plus the down force that this force is applying. So those two vectors together have added to give this vector. It doesn't matter how long we draw it because we're just indicating it on our diagram, and we need to understand what this normal force is. To resolve vectors with angles doesn't necessarily have to be to any scale or length when we're doing it algebraically or analytically, which is what we're doing. We're not drawing a scale drawing and using our ruler to measure a resultant force. We're just remembering that we have to make sure that angles are accurate. So we know that this angle here is 70, and then that makes that one 20. So this normal force here, just to reiterate, is the normal force of the object, the weight force, the vertical component of the weight force on the object, plus that vector there. Now, another misconception might be what the value of this force is. Now, a common misconception is that the frictional force applied to an object on this plane is always going to be the same. And that's not true. We know that through Newton's second law, that if we act upon a force, it's met with an equal and opposite reaction. So the friction that this plane is putting on this box is going to be equal to the force that it's acting against. So we're trying to pull up, right? We're trying to pull up, and the frictional force has to equal any forces that is trying to go up the plane. So the frictional force is not always the same for every object. And what I'm trying to say here is that the force that the friction is offering on the object not only is has been contributed by the downwards weight component of the force, but also this component of this force here. So the force that the plane is acting upon the box is contributed by the component of the force acting down the hill, but also this force here, right? And obviously those are two opposite forces, so they'll add to give something. One will be negative. But what I'm trying to say is that this vector here, right, has been contributed by the component of the weight force going down the hill, and it's been influenced by this component going up the hill. Now the reason I've said that is because this force along here will be the exact length, because the reaction force in the angle of repose, this reaction force here, is defined to be the angle, is defined to be the force. So the reaction force is designed to be the addition of the normal force and the frictional force. However, since this normal force and this frictional force was influenced by this force here, that force that was acting upon the object actually contributed to these numbers. The components of this force are within these numbers here. Because of that, the reaction force is going to be the correct length to make this force along here the base of this triangle, right? We also know that the weight force is going to act down here, and it's going to be the correct length because this normal force was contributed in the y direction by this mg component here. So the reason this will always be the correct length, we're not drawing something to scale, we're not doing a scale drawing like we have done in civil structures, we're not solving this question graphically. We're realizing that since this normal force and since this frictional force has been influenced by this force, then the reaction force actually has already this force taken into account, which means that this force here is the whole length of the triangle, and it will always be the correct length so that we can form this triangle here. I hope that makes sense. I couldn't figure out how to write that down and explain it to you, so I just thought I'd make a quick video. Oh, and of course, sorry, we arrive always with this triangle. So 20 plus the angle of repose. Again, since this reaction force, we had our normal force here, right? We had our normal force here. The mg cos theta of the normal force would obviously be that vector there. And then this force has altered the normal force, so it has this additional component here, as has the friction part, which was this part of this force. So since, again, just to reiterate, since this force has contributed to the normal force and the frictional force, when we calculated this reaction force, then this base of the triangle will always be the correct length so that we can draw it along here and then complete our triangle. I hope that makes sense. Just email back if it doesn't. Thank you.